starting up section 3.5. Go. What are we doing here? Okay, so we're going to pause for a moment with developing new derivative rules. We'll come back and learn more derivative rules for logarithms and general exponents in 3.6. And then we'll even learn some more rules in 3.11. Right here in 3.5, implicit differentiation. We're going to take what we know. We have, plenty enough derivative rules at this point to introduce a new idea. We're going to see all those rules in play, and we're going to take differentiation just to another level. So a lot going on in this section. What's this all about? Implicit differentiation. We're going to be taking derivatives of implicit equations. That probably sounds strange. What's an implicit equation? I've never heard of that. Actually, it's something that we've been working with for years and years. We just probably haven't used that kind of language before. So let's back up a little bit and define that. What's an explicit equation? An explicit equation is something that's been solved for y, and it would represent a function. So y equals such and such. An implicit equation is, well, the opposite of that. It has not been solved for y. So we don't have y isolated. It might be a function, it might not be. It could be that if you isolated y, you would get a function, but more times than not, it's not actually a function that you're working with. For example, let's look at this. X squared plus y squared equals 25. That's not solved for y, and it turns out it's not a function, even if you tried to solve for y. So that is an implicit equation. So what I like to do at this point is say, hey guys, x squared plus y squared equals 25. We've worked with stuff like that plenty, not in this course, but in pre-calc and even before that. What would the graph of x squared plus y squared equals 25 look like? And usually most people, there'll be several people in the class that know pretty much right away that that's a circle centered at the origin with a radius of 5. So there you go. Clearly not a function, does not pass the vertical line test. Does that mean we can't do anything with derivatives? We can work with derivatives here. Let's kind of think about it for a moment in the graph. There are obviously points all along the outside of that circle, or on the circle, I should say. Let's name one of them. So right there, there's the point 4, 3. 4, 3 would solve our equation, right? 4 squared plus 3 squared would equal 25. And we can see it plainly right there on the circle at the point 4, 3. Well, we can draw a tangent line there, right? We can draw a line that passes through that point and just grazes by the circle. So if we can draw a tangent line, we should be able to figure out what its slope is and all that. We should be able to find a derivative. How are we going to do that when we don't have a function? The only thing that we've been doing derivatives of so far are functions, obviously, right? Okay, check it out. Here's what we can do. To find the derivative of an implicit equation, we're going to call the derivative dy over dx. We like that Leibniz notation here. 2 steps. Step number 1 is to take the derivative of both sides of the equation with respect to x. So we're going to take the derivative of the left and say it's equal to the derivative of the right, both with respect to x. That makes sense. We're kind of thinking of a derivative a little bit differently here. We're thinking of the derivative not as like a new function that's based on the previous original function. We're thinking of it as an operation. Take the derivative of the left side and take the derivative of the right side. And so that's kind of a different way of thinking about derivatives at this point. You could argue that that's actually what we've been doing all along. If we had something like, I'll just take something easy like y equals x squared, well, then the derivative dy over dx equals 2x, like you could argue we're taking the derivative of both sides. But we didn't need to think of it that way before. Here there's no other way around it. We need to think of take the derivative of the left and it's equal to the derivative of the right. Okay, so we'll practice this in a minute. What would step number 2 be? Solve for dy over dx. That doesn't make a whole lot of sense at this point before we see an example. So let's get to it. I'm going to keep those 2 steps there on the screen. And we're going to apply that to our circle equation, x squared plus y squared equals 25. Okay, so how would this play out? Take the derivative of both sides with respect to x. I recommend beginning with this line right here. D over dx equals x squared plus y squared equals, and wow, I apologize. Little typo. I meant to put a d over dx of bracket 25 on the right side as well. So we're taking the derivative of the left. The d over dx means the derivative of what follows. So this is the derivative of x squared plus y squared would be equal to, and supposed to be a d over dx here, the derivative of 25. Okay. I like that step, writing d over dx to both sides, just because it causes us to slow down a little bit, kind of think about what derivative rules might be in play and how that's going to work. It's a good thing to kind of put on the brakes a little bit before you plow ahead. What does it mean to actually take the derivative of both sides, right? This is different. Well, we'll start with the left and we'll just go term by term. So the derivative of x squared with respect to x, there's nothing unusual about that. That's simply 2x. We're hopefully pretty familiar and comfortable with that. But when it comes to y squared, it's going to be a little bit different. What is the derivative of y squared with respect to x? And there's something we haven't seen before. We're going to take the derivative of a variable with respect to a different variable. How is that going to shake out? So it turns out we should take the derivative as normal, but then multiply by dy over dx in this case. So taking the derivative as normal would mean 2y. Then we're going to multiply that by dy over dx. Why is that? Let me pause here, go to my paper, and explain kind of a little bit more thoroughly why the derivative of y squared would, with respect to x, would result in what we see here. When you think about y squared, if we're taking the derivative with respect to x, we're thinking of the y as a dependent variable, okay, with respect to x. So this is our independent variable. Y is our dependent variable. That means when we take this derivative, we need to apply the chain rule. What? Why would we apply the chain rule? Because we need to think of y squared as being an inside function, the squared being the outside. That means when this derivative unfolds, the derivative of the outside, the 2 comes down, right? It drops to a first power, like 2y to the first, right? Then, so that would be the derivative of the outside. Then we need to multiply by the derivative of the inside. Here, the inside is simply y. Well, what's the derivative of y? Well, it's simply dy over dx, the derivative of y with respect to x. So we got the derivative of the outside times the derivative of the inside. The derivative of the inside, y, is, well, the derivative of y with respect to x, dy over dx. Okay, hopefully that clears things up maybe. At the end of the day, really what you need to know in order to execute problems is whenever I have a term involving a y, if I'm ever taking the derivative of a term that has a y in it, once I'm done taking the derivative, I need to multiply that thing by dy over dx because there was a chain rule involved, and this is the derivative of the inside the y. Let me explain it even a little bit deeper. What if we were taking the derivative of x squared with respect to x? We could actually treat it, believe it or not, we could treat this in the same way. We could treat this like a chain rule, right? So think of the 2 as the outside. So 2, copy the x, times then the derivative of x with respect to x is dx over dx, derivative of x with respect to x. It just so happens that dx over dx is equal to 1. So this would all simply become 2x, and that's the derivative we're familiar with. So we never write it or mention it because why would we? It's just always going to be equal to 1. But when the variables are different, well, now that's not the case, and we got to write like something like a dy over dx. Okay, I know that's weird. Takes us a little bit of time to wrap your head around it, but oftentimes that happens just with the practice. We kind of see it like, oh, okay, no, I start to see different examples, and you start to see this idea from different angles, and kind of gives you a little bit of time to process that. All right, so here we go. We got our left side derivative is 2x plus 2y dy over dx. The derivative of the right side, well, derivative of 25 is 0. So there you go. We've done step 1, take the derivative of both sides with respect to x. Now step number 2 maybe makes some sense. Solve for the dy over dx. We're going to isolate dy over dx in that equation. How would we do that? Well, let's begin by subtracting the 2x. And then we can divide by 2y. 2's cancel, and we get dy over dx equals negative x over y. Now, interesting. Notice that derivative involves both x and y. That makes sense because even, the implicit equation had both x's and y's in it. And so it makes sense that the derivative equation would involve both x and y. That's interesting. So what if, say, we wanted to know the slope of the tangent line at a certain point? So the point that we pointed out a moment ago was at 4,3, right? That point on the circle. How would we go about that here? Like, how would we find the slope of the tangent line at the point 4,3? Well, it turns out we're given the x coordinate and the y coordinate. So we can plug in x is 4 and y is 3. And so the slope of the tangent line going through the point 4,3, dy over dx equals negative 4 over 3, negative 4/3. If you think back to that graph a second ago, maybe I can even click back to it. There it is. There we are at 4,3. Yep, the slope, well, kind of have to take our word for it, but yeah, the slope of that line, it's negative, and it turns out it's exactly negative 4/3. What if we wanted to know the slope of the tangent line somewhere else? What about the point directly below it that's also on the circle, the point at 4, -3? They have the same x coordinate, but now we drop down and find the point on the circle below the x-axis. Well, same idea. We'll plug in the x, we'll plug in the y. Negatives would end up canceling here, and we'd get dy over dx equals positive 4/3. And that makes a lot of sense. On the circle, if we looked at this tangent line at 4, -3, it would be The same slope, just positive for that point down below, coming upwards. Okay, we've got some more examples here in a moment. We're gonna get a little bit more difficult. We'll do that in the next video.